Everyone. So let's talk a little bit about the difference between a tree that is binary, as in it happens to have two child nodes named left and right, and a binary search tree. So in order for something to be a binary search tree, and we've constructed one here manually, in order for something to be a binary search tree, um, it must be true that every node has only on its left nodes that are less than it, right? So 5, 7, and 3 are all less than 9. And then only on its right side, it has nodes that are larger, right? And so that must be true for every node in the tree in order for it to be a binary search tree. And so this is a binary search tree because, again, 5 is less than 9, 11 is greater, and then 7 is greater than 5, and 3 is less than 5. So in that way, we have a binary tree. Now, what would happen if we wanted to insert a node into this tree? So let's insert, for example, 19. So we'll just add 19 down here. And the reason for that is 19 is larger than 9, and it is also larger than 11. So we had to go right. That was the only direction that we could go in order to maintain it being a binary tree. If we wanted to insert 10, we would have to go, it's larger than 9, down to 11. Okay, it's less than 11, and so now we have 10 here. So that's what makes something a binary tree. And it's an efficient data structure for doing things like finding the maximum number, finding the minimum number. Many insertions into binary trees are pretty all right, but a lot of times you're going to have to rebalance them. We'll visit that in another video. So let's talk about how would we dynamically add something to our tree? Because right now we've constructed our nodes very particularly. We just said, tree.root.left and tree.root.right. So how do we make a method that makes these decisions for us given a tree that already exists? So we'll define an add function and we'll pass in self, of course, and node, the node that we want to insert. Now, the first thing we want to do is if root is none, then what we want to do is say self.root is the node, and then we're done here basically. But if that's not the case, if it's not the easiest possible solution, what we're going to need to do is create a recursive function to recurse down into the thing. So the first thing we want to do is we want to ask ourselves if the node dot data, because that's what we're comparing here is the data. If the node dot data is less than the self dot root, right? And that's the main thing that we're really doing here, right? But the thing is, we want to do it recursively, right? We want to kind of do the same thing over and over again to each node. And so we kind of need that like current root function. So I'm just going to say root equals self.root. And then I'm going to say def insert root and node is what we're going to pass in. And that way we'll just treat everything like it's the root. So if node.data is less than self.root, what we'll do is we'll just say if root, not self.root, but just root. If root dot left is none, then root dot left is node. Otherwise, we need to just call insert on root dot left and node. And then we'll do this again for the right. So, if this isn't true, if node dot data is not less than root dot data, then we're on the right hand side. So if root dot dot right is none, then we'll go root dot right is node. Otherwise, root dot right, insert into root.write code. So this is how we can arbitrarily insert things, right? So yeah, so if we look at this, we run this and we just make sure the code's not going to crash. Then we can call tree.add, and I can call it on node 10, and I can call it node 19, and then those should be placed properly here. So I added that. Let's see, did I properly call that in there? Oh, I didn't actually call insert, so do that. So we have this function here in this method, and then we'll call it insert on root and node. There we go. So now you can see it's in here 3, 5, 7, 9, 10, 11, and 19. So I could just, change these all to tree.add, and they will properly, yeah, there we go. I'll just change these to tree.add, and they will properly add to the right spot in our tree. And there we go. Let's run that. And we still get the same order, 3, 5, 7, 9, 10, 11, 19. So as long as you're running an in-order traversal and your binary tree is properly set up, then all of your nodes should come out in the correct order, right? If I wanted to go ahead and just say add, tree.add node 4, right? You'll note that it's also in order here. So it's really good for keeping something in order when you already have an order in mind, but you're not going to be adding things in order. So you could say tree.add node of 34, and you can do this as many times as you want, and it'll arbitrarily handle however many as you want it to have, so long as there's not any duplicates. That's very important. 340. There we go. So now all of our numbers are still ordered. 3, 4, 5, 7, 9, 10, 11, 19, 32, 34, 56, 94, and 340. Just because we're doing an inner order traversal and we're using this method to add things to our tree. So yeah, that's how a binary search tree works, and that's how you add things to it.